Okay, let's solve this problem together. We have an adiabatic nozzle, and air enters this adiabatic nozzle. So to solve this problem, nozzle has an inlet and exit, so it's an open system, steady state, open system. Then the energy balance equation for this steady state open system is Q dot in plus W dot in plus M dot at the inlet. So let's assume that the inlet is number 1, exit is number 2. M dot at the inlet number 1. This mass at the inlet has enthalpy, specific enthalpy H1, and specific kinetic energy, velocity square over 2 plus potential energy, gravity times elevation Z1 is going to be the same as energy transfer out of this control volume per time. So we can first consider the rate of heat transfer Q dot out, the rate of energy transfer by work, and the rate of energy transfer by mass at the exit number 2. So we have the mass flow rate at the exit M dot number 2, and this mass has specific enthalpy H2, specific kinetic energy, velocity square over 2, and potential energy, gravity times elevation Z2. So this is the general energy balance equation per unit time whenever we have a steady state open system. So we can simplify this energy balance equation for this nozzle. First, we can say the elevation is about the same. Then we can neglect potential energy change. And there is no energy transfer by work, so you can neglect W dot in and W dot out. And it says not just a nozzle, it is an adiabatic nozzle. This means there is no heat transfer. So you can neglect Q dot in and Q dot out. And we only have one inlet and one exit. So the mass flow rate at the inlet should be the same as the mass flow rate at the exit. So we can just say M dot instead of M dot number 1 or M dot number 2, we can just say M dot. Then we can remove this subscript here. Then divide each side by M dot. Then you can neglect M dot. Then the remaining is the sum of specific enthalpy and kinetic energy. Should be the same. So this is the mass balance equation, and the energy balance equation is QH1 plus V1 square over 2 is H2 plus V2 square over 2. We can move specific enthalpy to the left-hand side. We can move kinetic energy to the right-hand side. Then we have H1 minus H2 is velocity 2 square minus velocity 1 square divided by 2. So this is the energy balance equation we can use for this control volume. Okay. So we have two governing equations. The first one is mass balance, and the other one is energy balance. Okay. So now let's find out, what we need to determine in this problem. We need to determine the mass flow rate through the nozzle. Then how can we determine this mass flow rate? There are two different ways to determine mass flow rate. M dot can be determined by the density times volumetric flow rate. Or we can determine M dot by density times average velocity times cross-sectional area. In this problem, we have velocity and cross-sectional area at the inlet. So we have this velocity V, which is 45 meters per second. And we have this cross-sectional area, which is 110 centimeters square. But we do not like centimeters. We want meters. So 100 centimeters is 1 meter. So we have a square here. 10,000 centimeters square is 1 square meter. So that's how we can determine velocity and the cross-sectional area. But we do not know the density. So how can we solve this problem? We know the temperature and pressure. If you know temperature and pressure, we can determine another property of this pure gas. If we assume that this air follows the ideal gas behavior, then we can use PV RT. This is the ideal gas equation of state. And this V, this lowercase v, is the specific volume, which is the inverse of this density. So we can rewrite this pressure divided by density is gas constant times temperature. In this problem, we know the pressure that is given, 300 kilopascal. And temperature, gas constant R, can be determined by universal gas constant R bar divided by molecular weight of this gas. By the way, this is air, so molecular weight of air. Then gas constant R is going to be always 8.314 kilojoule per kilomole Kelvin, and the molecular weight of air can be found from this table, table A1. So this is table A1. Air, the molecular weight is going to be 28.97. kilogram per kilomole. So that's how you can determine the gas constant of air. By the way, air is one of the most widely used substances in thermodynamics. So you may want to just memorize the gas constant of air. That is 0.287 kilojoule per kilogram Kelvin. If you do the calculation here, 8.314 divided by 28.97, And the temperature. What is the temperature? 200 degrees Celsius. So this is 200 degrees Celsius, right? No, no, you don't use Celsius, right? You have to use Kelvin when you use ideal gas equation. So this is 473 Kelvin. So if you solve this ideal gas equation, you can determine the density of the system. And once you determine the density of the system, you can determine the mass flow rate. Of this air, and the mass flow rate is 1.094 kilogram per second. So that's how you determine the mass flow rate of this air in the nozzle by using density times velocity times the cross-sectional area. And since density was not available, we used this ideal gas equation to determine the density, and we can get the mass flow rate. So that was the first problem, the mass flow rate. The first problem, the mass flow rate through the nozzle. And what is the second problem? The exit temperature of the air. And how can we determine the exit temperature? Can we use this ideal gas equation? Unfortunately, we know pressure and temperature, but we do not know the specific volume at the exit. So we cannot use this ideal gas equation. Then, what about this energy balance equation? The left-hand side of this energy balance equation is H1 minus H2. How do we determine these specific enthalpy values? If you have a phase change material, we can use the table. You remember the last problem in your first exam. If you know two properties, then you can determine any other properties in the system. We just need to determine the phase change process and go to appropriate table to determine an unknown property. That is for a phase change material. However, this one we have air. So if you have air, such as pure gas, we can use specific heat. If you don't remember how to use the specific heat, U2 minus U1 is CV T2 minus T1. H2 minus H1 is CP T2 minus T1. So that's how we use specific heat. Then what is specific heat? This is CP and CV, they are specific heat. Then, if we want to determine H1 minus H2, we can use CP. So this equation becomes CP T1 minus T2 is velocity 2 square minus velocity 1 square divided by 2. Then, according to the problem, we know the temperature at the inlet 200. Temperature at the inlet is 200. So this one is 200 degrees Celsius. And the exit velocity is 180 meter per second. The inlet velocity is 45 meters per second. So we have temperature and the two velocities. So if you know the specific heat Cp, we can determine the final temperature. So then how can we determine this Cp? We can go to table A20. If you go to table A20, you can determine Cp of air. Cp of air is the second column in the table. So sounds, the pretty straightforward. We just need to determine the specific heat and we can solve this T2. However, there is a problem. The specific value is not just one. There are many specific heat values. Why is that? Because this specific heat is a function of temperature. When temperature goes up, in this case, specific heat goes up. So then at what temperature, then you need to determine at what temperature you are going to evaluate this Cp. We have to use the average temperature. You may remember in the last problem, we used the average temperature between the inlet and the exit to evaluate the specific heat. So, sounds simple. Let's determine the average temperature. What is the average temperature? Unfortunately, we only know the initial inlet temperature. The exit temperature is what we want to determine. Therefore, we cannot find the average temperature because we do not know the final temperature. Then we are stuck, right? So how can you solve this problem? If you are a computer, then we can say, oh, there's an unknown, the value. So that's an error, right? But we are human, we are engineer. So we can find a solution. What is that? We can guess the exit temperature and solve the problem. Then what if we made the wrong guess? After you solve the problem, you can check if your guess makes sense depending on the final temperature you guessed, right? So you are going to guess the exit temperature and solve it, and you will determine the exit temperature. Now you can verify, whether your guess is close to the final answer or not. If they are close, then you did a good job. If they are far away, no problem. You can do a second guess. But in the second guess, now you're not going to choose any random value. You can choose the answer from the first guess as the second guess. That is called iteration. So if you have, if you need to, if you cannot solve a problem because there is an unknown value, then you can use this iteration method. That is how computers solve a problem numerically. Okay. So let's see. Let's do it together. So the inlet temperature is 200 degrees Celsius. But if you look at the the unit of this temperature on this table, it is Kelvin. So so this is 473 Kelvin. Now I'm going to guess the exit temperature. What about room temperature? 20 degrees Celsius. Okay, so I'm going to guess. So first guess. So first iteration. I'm going to say T2 is maybe room temperature, 300 Kelvin. So that is my assumption. So based on this assumption, let's solve this problem. So what is the unknown? We need to determine this Cp so that we can solve this energy balance equation. So to determine this Cp, we need to know the average temperature. So what is the average temperature? 300, 473. So the average temperature is 773 divided by 2. So that is 786 or something Kelvin. Then what is the specific heat at this temperature? It's going to be between 350 and 400. So we need to do a linear evaluation, a linear interpolation. So let's assume that we did it. So the value is going to be approximately 1.011 or something. So at this average temperature, specific heat is going to be 1.011 kilojoule per kilogram Kelvin. So using this specific heat, we can solve this the energy balance equation to determine T2. So let's do that. Need a calculator. $180 square minus 45 square divided by 2,000. 15.1875, and the specific heat is 1.011. So we got 15.02. So that is from 473 minus 473. So we get 458. So the exit temperature so if you solve this problem, we get the exit temperature T2 is 457.98 Kelvin. So this is how you determine the exit temperature. Are you satisfied? No. Why is that? We have to make an assumption to solve this problem because T2 was not available, because otherwise we couldn't get this specific heat. So we assume that T2 is 300, and then what we got for T2 is going to be 458. Are they close? I don't think so. So our assumption was not okay. So what can you do? So first iteration was not okay. So we can do, the second guess. Second, now we are going to assume the exit temperature T2 is going to be the same as the answer from the first iteration, 458 Kelvin. Now let's solve it again. The second time, let's hope that this time we get the final answer close to this guess. Then what is the average temperature? The average. 458 plus, what is the inlet temperature? 473 divided by 2. We got 465. at 465, if you do a linear interpolation, we are going to get approximately 1.023. The average temperature is 465.5 Kelvin. At this temperature, Cp can be found, and it is 1.023 approximately. Then using this specific heat, we can solve this energy balance equation one more time. So let's do that. 180 square minus 45 square divided by 2,000. So that's a 15.18 divided by 1.023 minus 473. I get 458.15. So from this, T2 is 458.15 Kelvin. Now, are they close? Yes. So you can say the exit temperature is going to be 458. Any question about this iteration method? The last problem is the exit area of the nozzle. Exit area. So how can we find this exit area? So there are several equations here, and which equation has exit area? This energy balance equation? No, there is no area. This m dot? Yes, there is an area. So we can use this equation. So m dot is density times average velocity times cross-sectional area. So there is exit area. Then do we know the mass flow rate? Yes, 1.094. Wait a minute, isn't it the mass flow rate at the inlet? Yes. Can we use the same value at the exit? Yes, because of conservation of mass principle. So this mass flow rate at the inlet exit is going to be 1.094 kilogram per second. What about the velocity? The velocity is given. The exit velocity is 180 meter per second. 180 meter per second. Then can you determine the exit area? Not yet, because the density is not available. So let's find density. How can you find density? Is there any equation that has density? Yes. T over density is RT. So we can use this ideal gas equation. Wait, did we already use this ideal gas equation? Yes, but only at the inlet. You can use this ideal gas equation again at the exit. So let's do that. P over rho is RT, but this time at the exit. What is the exit pressure? (100 kilopascal is exit pressure. So this one is 100 kilopascal. What is the gas constant? 0.287 kilojoule per kilogram Kelvin. What about the temperature? Oh, we found the temperature from the previous problem, 458.15. 458.15 Kelvin. So we have everything. We know now you can determine the density. Once you determine the density, you can substitute this density value into this mass balance equation to determine the cross-sectional area. Okay? Any question? What is the final answer? Unfortunately, I do not know. The solution is wrong. They made a mistake. But you can calculate, right? Any question about this problem? So what you need to think now is, if I give you this problem in your second exam, can you solve it? So practice this problem until you can say, oh, if I see this problem or similar, I can do it in the second exam, okay? As you observed in my first exam, you know, my second exam is going to be also in the same format. Problems are going to be similar to the homework assignments and the problems in the classroom. Okay, so there's no surprise. So if you put enough effort, then you can get 100 out of 100. Of course, the total is going to be 30 points, so you can get 30 points out of 30. Any question? No? Yes. Yes, it was given in the problem. Inlet pressure, exit pressure. Okay, then let's go to the next problem. Turbines and compressors. One of the most widely used thermodynamic devices in the industry. What is turbine? Turbine is a device to convert thermal energy into mechanical energy. Where do we use turbine? To produce electricity. To produce electricity, we use turbine. So we provide thermal energy by burning, the fossil fuels, or by, having nuclear reaction, or by concentrating the sunlight, or by, collecting, the heat from underground, such as geothermal power plants. So we get those heat, and then using that thermal energy by turbine, we can produce mechanical energy, such as shaft work. Then this shaft is going to be coupled with generator. That's how we produce electricity. Of course, there are other forms of, the power conversion available in the world, but the majority of power production is done by turbine. Okay, So we got that. What about compressor? Compressor is a device that we use a lot, usually in a refrigeration system. So we use compressor in this air conditioning unit. We use compressor in refrigerator or freezers. So these two are ones of most widely used engineering devices. But we may want to know, how this turbine and compressors work. So it's pretty simple. Turbine looks like this. And there's an inlet here. And there's an exit here. And there's a shaft. Would be connected to generator. And this shaft has lots of blades, turbine blades. Not like that, you should see a lot of turbine blades. Then what's going to happen? So turbine converts thermal energy into mechanical energy. We all know what is mechanical energy. The mechanical energy is going to be this shaft work. W dot out. So how can we produce this shaft power? By providing thermal energy. Then what determines thermal energy? There should be a working fluid, and that should have a lot of thermal energy. When a substance has a lot of thermal energy, what happened to their properties? You should expect low pressure? No, high pressure. Low temperature? No, high temperature. So let's assume that the working fluid is steam. Then this steam should be at high pressure and high temperature. So how can we, produce high temperature, high pressure steam? By heating water, right? How can we heat water? By burning fossil fuel. That's how we use, how we produce electricity. By having nuclear reaction, by concentrating the sunlight. So that's how we produce high pressure, high temperature steam. Then this high pressure, high temperature steam enters this control volume. Then what's going to happen? What do you think this steam want to do when it is under high pressure and high temperature? It wants to expand. So when it enters here, so there's a steam, which direction this steam can expand? This way? No. This way to go outside? No, that's the inlet to go in, right? So there is more steam is coming in. So there's no way going out. So the only direction for this expansion is going to be this way. So this steam expands this way. Then there are, these turbine blades. What happens? Why steam expands in this way? It's going to rotate. It's going to push each turbine blade. It looks like a fan. So it's going to rotate due to the expansion. Then at the exit, we have low pressure, low temperature steam, or even condensed water exits. The turbine. So that's how we convert thermal energy into mechanical energy. Okay, so that's turbine. So in this turbine, thermal energy becomes mechanical energy. That's not it. In this slide, we have turbines and compressors. Then why do we, study compressors too? Because they look similar. Turbine is a device to convert thermal energy into mechanical energy. On the other hand, compressor is a device to convert mechanical energy into thermal energy. And this compressor looks similar to the turbine, but it looks the opposite of this turbine. So there's an inlet, there's an exit, and this compressor does not produce work, it consumes work. So we need to provide mechanical work, W dot in. Then let's see what happens. So there's an air goes in. So air is going in. So air is here. Now this shaft is rotating due to the external work. Then what's going to happen? This fan is going to push this air into this direction. And if you can see, you get smaller volume. So what happens? Its pressure goes up. When pressure goes up, what happened to its temperature? Goes up too. So at the exit, we have high pressure, high temperature. Air is at the exit. At the inlet, we have low pressure, low temperature. So you can see pressure and temperature of this air increased due to this compressor. And what does it mean when pressure goes up and temperature goes up? The thermal energy of this air has been increased due to this compressor. So that's how turbines and compressors work. They look similar, but they are, the opposite of each other, right? And all they do is conversion between thermal energy and mechanical energy. So one case, we are producing work. One case, we are consuming work. Okay? Any question about the concept of turbines and compressors? Then now, let's study how to, so that's the physics of turbines and compressors. So now we are going to talk about what? Whenever you study on engineering, we first talk about physical phenomena, and then we talk about mathematic expression, right? So we first studied the physics of this turbine and compressor. Now we understand that. So let's write the mathematics of these two. Then are they difficult? Not at all. Not at all. You already know how to write the general energy balance equation for steady state open system. You always start from there. So that when you have steady state open system, this turbine is a steady state open system. This compressor is also steady state open system. When you have steady state open system, the energy balance equation is going to be always Q dot in plus W dot in plus M dot at the inlet. So let's assume that inlet is number 1, exit is number 2, inlet is number 1, exit is number 2. Then M dot at the inlet, this one has what? There are 3 energy each mass has. Specific enthalpy H, kinetic energy, velocity square over 2, and potential energy, gravity times elevation Z. So these are energy transfer into this control volume. Heat transfer, energy transfer by work, energy transfer by mass. But energy transfer by mass, there are three energy transfer by mass: enthalpy, kinetic energy, and potential energy. What about at the exit? Not at the exit. What about energy transfer out of this control volume? First, we can consider heat transfer, but this one goes out, Q dot out, and energy transfer by work, W dot out, and energy transfer by mass at the exit. M dot exit is number 2, M dot number 2. This mass has enthalpy, kinetic energy, and potential energy. So this is the general energy balance equation for steady state open system. Now we are going to simplify this energy balance equation for this turbine and for this compressor, both of them. So turbine first, I'm going to use this red. So for turbine, when we run a turbine, do we heat turbine? No, there's no reason to heat turbine. So we usually do not heat turbine. So there's no Q in. Do we provide work to run a turbine? No, turbine is a device to produce work, not consuming work. So we produce work, but we do not consume work. And we usually neglect kinetic energy change and potential energy change. So what about heat transfer from the turbine to the outside? It depends on how much insulation does it have. So sometimes there is a heat loss, sometimes there is no heat loss. So this Q dot out is case by case. Triangle. So the energy balance equation for turbine is going to be, oh, by the way, how many inlets, how many exits? There is only one inlet, one exit. What is the relation between the mass flow rate at the inlet, mass flow rate at the exit? They're the same. So m dot number 1 should be the same as m dot number 2. So it's just m dot. M dot H1 is possibly Q dot out. This is case by case. Plus W dot out plus M dot H2. So that is turbine. If we move this one to the left-hand side, turbine is going to be M dot H1 minus H2 is possibly Q dot out. You can neglect that if you have an adiabatic turbine system, plus W dot out. So this is the energy balance equation for a turbine system. Any question up to here? That's all for turbine. That's all mathematics that you need to know in terms of turbine. If you don't have a question, let's move on. Let's move to compressor. As I told you, compressor is a device to, convert mechanical energy to thermal energy. So we consume mechanical power and we increase the thermal energy of this working fluid. So as a result, pressure and temperature of the working gas goes up. So let's talk about this, the compressor on this energy balance equation. So this time it's a compressor. Blue. So Do we heat compressor? No way. There is a power goes in. There's a work input to run this compressor, right? Yes. And there is a enthalpy at the inlet. Yes, there's something goes in, but we usually neglect kinetic energy change, potential energy change. And there is a energy by mass at the exit, and compressor cannot produce work. There's a possibility, the heat loss to the surrounding, depending on the insulation of this compressor. So the energy balance equation for this compressor is going to be this one. W dot in, let's move this one to the right hand side. It's going to be Q dot out, this is case by case, plus M dot H2 minus H1. So this is the energy balance equation for this compressor. That's all. Then what do we do now? Always there are three, the stages, each device. First, we talk about the physics of these systems, and then we talk about the mathematics of these systems. What is the third? We solve problems. So there is a problem here. Refrigerant R134 enters. By the way, just let me know if I'm going too fast or too slow. Or if it's just right. You can also say, oh, you're doing great. So R134A enters a compressor at 180 kilopascal as a saturated vapor with a flow rate. So we know the condition at the inlet, we know the flow rate, we know the condition at the exit. Pressure is 700 kilopascal. The power supplied is also given 2.35 kilowatt. We want to know the exit temperature. Okay, we can do that. So to solve this problem, first we come up with the physics of this compressor. So there is a physics of the compressor. So compressor looks like this. Has inlet number 1, has exit number 2, and at the this one consumes power because compressor converts mechanical energy into thermal energy. So thermal energy is given to the working fluid entering the compressor. So at the exit, this one has high pressure, high temperature. Okay, so then what do we know at the inlet? 180 kilopascal. P1 is 180 kilopascal, and it is saturated vapor. Phase change process number 4, saturated vapor, and the flow rate. That's not mass flow rate, that's a volumetric flow rate. So mass flow rate at the inlet is 0.35 cubic meters per minute. Now you know what to do. If you have a flow rate, you need to determine mass flow rate. Just for your information, why can't we just use flow rate instead of mass flow rate? Why is that? What kind of conservation laws that we studied? Energy conservation, mass conservation, and what about this volume? Is there conservation of volume principle No, that's why we want to use mass flow rate rather than volume flow rate. Okay, because volume is not conserved. So if you use this volume flow rate, this is not the same as the volumetric flow rate at the exit. But if you convert this one into mass flow rate, that mass flow rate is constant. Conservation of mass principle. What about at the exit? We know the pressure is 700 kilopascal. P2 is 700 kilopascal. And the work power produced, provided to the system is 2.35 kilowatt. And we want to know the temperature at the exit. So what is T2? That's the physics. Now let's talk about mathematics. We have a turbine. We have a compressor. So this is the energy balance equation. This is the mathematics for this compressor. So let me write it down here. So the governing energy balance equation is W dot in is Q dot out plus M dot H2 minus H1. So that is the energy balance equation for this compressor written here. Then we are ready to solve this problem. So we wrote the schematic of this compressor. We wrote the governing equation. So then, now let's solve this governing equation. First, what is W dot in? Oh, that is given. 2.35. Okay, good. What about Q dot out? Is there heat loss from the compressor? There's no information, then you can neglect heat loss. So it's an adiabatic compressor. What about M dot? Oh, we can find this M dot from this volumetric flow rate. What about H1? Oh, we can get this H1 from P1, and it is a saturated vapor. So P1, H1 is going to be Hg, saturated vapor. Then solving this equation will give us H2. If you know T2, H2, can you determine T2? Yes, a simple table problem in the first exam. So that's plan. So let's find M dot first. How do we determine M dot? There are two different ways. M dot can be determined by density times volumetric flow rate, or density times velocity times cross-sectional area, but we know there's a volumetric flow rate. So we just need to determine the density at the inlet, because we know the volumetric flow rate at the inlet. So how do we determine the density at the inlet? We know it is a saturated vapor. By the way, this is density. In thermodynamics, we use specific volume, right? Specific volume. Then how do we determine specific volume? By the way, density is the inverse of specific volume. Then how do we determine the specific volume? It is saturated vapor. If you have saturated vapor, the specific volume is Vg at the given condition. What condition? 180 kilopascal. 180 kilopascal. That's how you determine specific volume and the density. What is Vg at 180? You need to go to saturated R134A pressure table. Where is it? Table A11, properties of saturated R134A pressure table. And there is a 180 kilopascal because 1 bar is 100 kilopascal. 180 kilopascal is 1.8 bar. And what is VG? Right here, 0.1098. 1 over 0.1098 cubic meters per kilogram. Now we get the density. Goes in here. Now we just need to determine the volumetric flow rate. The volumetric flow rate is 0.35. But look at the unit. I don't like that unit. So the volumetric flow rate is 0.35 cubic meters per minute. Oh, minute? We don't like minute. We prefer seconds. So 1 minute is how many seconds? 59? Yeah, 59. No, 60 seconds. We want to live longer, right? So from that, you can determine the mass flow rate. So from this calculation, you get m dot. What is it? 0.0531 kilogram per second. Just for your information, again, do not trust your solution. Look at that. These values are all wrong, so I recalculate them. Okay? Just for your information. Do not use solution. You can solve it because thermodynamics is super easy, isn't it? Yes, right? Okay, so if we got m dot, this one goes in here. So we got this one. What about H1? Oh, wait. H1 is the specific enthalpy of saturated vapor. It is saturated vapor. So we know how to get this one. Saturated vapor, the specific enthalpy of saturated vapor is Hg. At what condition? 180. So what is the value? Hg at 180 kilopascal, this number, 239.71 kilojoule per kilogram. So we have everything. Can you determine H2? Yes, you can. So from this equation, H2 is 283.97 kilojoule per kilogram. So we solved it. Am I right? Not yet. We want to know the temperature at the exit. But we got H. But that's okay. We know pressure and H. If you know two properties, you can find any other property, right? So we know 700 kilopascal, 283.97. So P2 is 700 kilopascal. So can you determine temperature T2? Yes. Oh, the last problem in your first exam, you remember the table problem. That's how we do. So to determine temperature, we need to know what? The phase change process. Oh, isn't it saturated vapor? Not anymore. It was saturated vapor at the inlet, not at the exit. So we don't know the phase change process at the exit. So to determine the phase change process at the exit, what we need to do? We need to make, since we know P T something diagram. So what diagram? TV, TU, TH. Since we know H, it's going to be, the good idea to make TH diagram, even though we prefer TV diagram. We like television. No? So at 700 kilopascal, so TH diagram looks like this. So to complete this TH diagram, we need to know Tsat, HF, HG. Where can we find Tsat, HF, HG? From 700 kilopascal. I don't have 700 kilopascal. Don't worry about that. I have a backup property table. So table A11. 700 kilopascal. Tsat is 26.72. 26.72 degrees Celsius. And HF, HG, this one and this one. 86.78, 261.85. So let me write these two values here. HF is 86.78. HG is 261.85. So on this pH diagram, there's 1, 2, 3, 4, and 6, right? No, 5. Now we need to determine the phase change process. So we made this pH diagram using this pressure. So it's time to use the other property we know. H is 283. Where is H? On this horizontal axis, 283 is greater than 86, is greater than 261. So 287 is somewhere on the right. So what is the phase change process? Number 5, superheat vapor. So if you know you have a superheat vapor, you go to superheat vapor table. This is the superheat vapor table. And this one is H, U, and V. There's a temperature T. So what is our H value? 283 is between these two numbers. So the temperature is going to be between these two numbers. So how can you determine the temperature? Can you say, oh, it should be between 40 and 50? That's not right. You need to do a linear interpolation. How can you do a linear interpolation? Temperature between 40 and 50, H between 275.93, 286.35, and what is the H value that we have? 283.97, the top left on the right. So top left on the left should be the unknown temperature T2. So if you solve it, you get T2. Oh wait, it's not complete. What about the here and there? You use the number in the denominator. 50, 286.35. So if you solve it, you get T2. So what is the final temperature? 47.71 degrees Celsius. That's how you solve this problem. If I give you this problem in your second exam, can you solve it? Now, yes, right? So I guess that's all for today. And next Tuesday, we are going to continue So this one was a compressor. Maybe next Tuesday, we are going to study a turbine system. That's all. Thank you. See you later. Next Tuesday.